Welcome to Spring LIB.
All right, so this is a Claisen condensation question, sort of in disguise. What we need to notice is that on this molecule, we have two ester groups. There's one there, 1, 2, 3, 4, and there's one here. And we're basically reacting it with a strong base, right? Whatever the same RO group here for our ester is. And then later treating it with cold dilute acid. It doesn't say that, but that's the condition for the Claisen condensation. And so recall that what we're going to look at on either of these esters is look at their beta carbon and see if they have an enolizable proton. And both do. Now the question in terms of which one is more likely to be deprotonated, right? Recall that this will form a carbanion after it's deprotonated. And tertiary carbanions are less stable than secondary carbanions. Right? It's the opposite of carbocations. That is to say that this secondary beta hydrogen is more acidic than this tertiary beta hydrogen. So we're not going to see deprotonation of this hydrogen. We're going to see deprotonation of this hydrogen. Okay. And this will form a carbanion, right? And that carbanion will attack this carbonyl. The carbonyl will then, in the next step, push back down to reform, and it'll kick off this ester group. Okay. So in short, what we're going to get is a bond between this carbon I'm highlighting in blue and this carbon I'm highlighting in green. And we're going to lose this ester group, but everything else will remain the same. So I think the easiest way to do this is I'm going to draw it again, and then I'm going to number the carbons so we can make sure. We're going to form a ring, right, because we're kind of joining two carbons that are joined through another set of carbons already, right? So we know we're going to form a ring. So what I like to do is number things so I can see how many members that ring will have after it forms. So I'm redrawing this 1, 2, 3, 4, like so. Okay, so how many members will the ring has? Well, we know it's going to start at this carbon or include this carbon, 2, 3, 4, 5, 6, and end on carbon 6. So it's going to be a 6-membered ring. So I'm really going to have two 6-membered rings joined here. Right. And then what's going to be sticking off of them? Well, on carbon 6, let's see, this is carbon 4, this is 5, that means this is 6, this is 3, this is 2, this is 1. So on carbon 6, we'll still have our double bond to oxygen. We'll no longer have our OR. And on carbon 1, we're going to have a bond to basically that entire ester group. Is what's going to be sticking off of carbon 1. Like so. And if we look around here, that looks an awful lot like option 1 to me.